Welcome to finding more of finding eigenvalues and eigenfunctions. So let's consider the boundary value problem, y double prime plus lambda y equals 0 with boundary conditions y of 0 equals y prime of L equals 0. Note here I've mixed up one end, it's the boundary condition on y. The other end, it's the boundary condition on y prime. Our job again is to find the eigenvalues and eigenfunctions. So let's go ahead and start off with lambda less than 0. So for lambda less than 0, we'll set lambda to be equal to negative omega squared. And we are looking at y double prime minus omega squared y is equal to 0. And this has general solution y equals C1 e to the omega t plus C2 e to the negative omega t. And we have y prime equaling C1 omega e to the omega t minus C2 omega e to the negative omega t. Plugging in our boundary conditions. So plugging in y of 0 equaling 0, we get then that 0 is equal to C1 plus C2. Plugging in y prime of L equals 0. We get that 0 is equal to C1 times omega times e to the LT minus C2 omega e to the negative LT, which can simplifies to 0 is equal to C1 omega minus C2 omega. The only solution to this system, so using these two equations here, we just wind up getting that C1 and C2 have to be equal to 0. The only way for that system to have a solution is the case where C1 equals C2. They're not linear combinations of each other, those two equations. For lambda equaling 0, we're looking at y double prime is equal to 0. So again, we have that y should be equal to C1 plus C2x or C2t. Sorry, I've been swapping back and forth my variables, I think, in these various videos. We have y is equal to C1 plus C2 times t. And this gives us then that if we plug in y of 0 equals 0, we are looking at 0 is equal to C1. I need to give myself just a little more room. So now if we go ahead and plug, this means since C1 is equal to 0, this means that y is simply C2 times t. We have that y prime is simply equal to C2. So if y prime of L is equal to 0, then that means that we have 0 is equal to C2. And so we have 0 is not an eigenfunction either. Is not an eigenvalue, sorry. So lambda equals 0 is not an eigenvalue. I should have mentioned earlier, since we got C1 equaling C2 equaling 0, we have that lambda less than 0 is not an eigenvalue. If we now take a look at the case where lambda is greater than 0, Again, we'll go ahead and set lambda to be omega squared. Then we have y double prime plus omega squared y is equal to 0. This tells us that we have general solution y is equal to c1 cosine of omega t plus c2 sine of omega t. Plugging in y of 0 equals 0. We wind up getting that 0 is equal to c1. And so we know that y is equal to c2 times sine of omega t. Then we have that y prime is c2 omega times cosine of omega t. So if we plugging in y prime of L equals 0, we are looking at 0 is equal to c2 times omega times cosine of omega times L. So to have a non-trivial solution, we get that cosine of omega L must be equal to 0. So this means that omega must be equal to an odd multiple of pi over 2. So we have 2k minus 1 over 2, or 2n minus 1 over 2 times pi. Again, the even multiples will land us on the integers, right? And so we need to do odd multiples over 2 and then multiply by pi. Here, n is a positive integer. So we wind up getting that we have eigenvalues lambda n equaling omega squared. So we have 2n minus 1 over 2 all times pi. Sorry, I didn't. Omega L would be equal to that. So omega would be that divided by L. So we'd get 2n minus 1 divided by 2L. Divided by 2L times pi, that whole thing squared. And our eigenfunctions we were left with, again, y was equal to c2 times sine of omega t. So our eigenfunctions will be phi sub n equals sine of 2n minus 1 times pi over 2L times t. Again, here, n is a positive integer. So in the case where our boundary condition is y of 0 equals 0 and y prime of L equals 0, this is what we get for our eigenvalues and eigenfunctions. We're going to now look at one more case, the last case I have saved for you as your weekly discussion. So the remaining case we're going to cover here, we'll look at the case where we have y double prime plus lambda y equals 0, with y prime of 0 is equal to 0 and y of L is equal to 0. Again, our job is to find the eigenvalues and eigenfunctions. So once again, we'll start off with lambda less than 0. Then we'll go ahead and set lambda to be negative omega squared. We are looking at y double prime minus omega squared y is equal to 0. And once again, we get that y should be equal to C1 e to the omega t plus C2 e to the negative omega t. We have y prime is equal to C1 omega e to the omega t minus C2 omega e to the negative omega t. Plugging in y prime of 0 equals 0. We get 0 is equal to C1 omega minus C2 omega, which essentially boils down to C1 minus C2 equals 0. Plugging in y of L equals 0, we are looking at 0 is equal to C1 e to the LT plus C2 e to the negative LT. And we wind up with, again, this system has the only solution C1 equals C2 equals 0. I just realized in the previous problem, I should not have divided through by e to the LT. We should have just left it with our e to the LT and e to the negative LT because they had, I did not have a common exponential to divide through by, but the concept is still the same. That's either way. In our negative eigenvalue case, we always get that C1 and C2 have to equal 0. All right, so continuing on with the problem I was working with, we don't have any negative eigenvalues. So lambda less than 0 is not an eigenvalue. Moving on to lambda equals 0. We are looking at y double prime is equal to 0. Once again, that means that y should be equal to C1 plus C2 times t. So from here, we wind up getting, plugging in. Oh, so y equals C1 plus C2 times t. We have y prime is just equaling C2. Plugging in y prime of 0 equals 0. Then we wind up getting that 0 should be equal to C2. Plugging in y of 0 equals 0. We get, sorry, y of L equals 0. Then we have y equals C1. So y of L equals 0 equals C1. And again, we have 0 is not an eigenvalue. Finally, we look at the case where lambda is greater than 0. For lambda greater than 0, once again, we will set lambda to be omega squared. We are looking at y double prime plus omega squared y is equal to 0. We know this has general solution. Y is C1 times cosine of omega t plus C2 times sine of omega t. We also have that y prime is negative C1 omega times sine of omega t plus C2 omega times cosine of omega t. Y prime of 0 equaling 0 means that we have 0 is equal to C2 omega times 1. So 0 is equal to C2 omega. And we get that C2 has to be equal to 0. So this means that our y is just C1 cosine of omega t. Y of L equaling 0. Then we have 0 is equal to C1 cosine of omega times L. So to have a non-trivial solution, we have cosine of omega L has to be equal to 0. So this means then that we have omega times L should be equal to 2n minus 1 times pi over 2. Again, that's the odd multiples of pi over 2. So we get that omega should be 2n minus 1 times pi over 2L. So here we have eigenvalues of lambda sub n equaling 2n minus 1 times pi over 2L, the whole thing squared. Our eigenfunctions in this case we had that y was equal to cosine of omega t, essentially was what we had boiled down to. So our eigenfunctions will be phi sub n equaling cosine of 2n minus 1 pi over 2L all times t. I've been using t's. You also can absolutely use x's. I kind of use them interchangeably. But this is how we can go about solving for our eigenvalues and eigenfunctions for boundary value problems with these specific boundary conditions. Again, I've now covered 4 of the 5 boundary condition cases I talked about. That last case will pop up in your weekly discussion.